Picture this. You find a photograph of your great-great-grandfather, but it was taken a full decade before he was even born. Impossible, isn't it? It completely shatters the laws of logic and time. That's essentially the predicament astronomers found themselves in when they pointed the most powerful space telescope ever built, the James Webb, toward the darkest, most remote corners of the universe. They fully expected to spot cosmic infants, dim, chaotic, newly forming galaxies. Instead, what they witnessed was something scientists are calling the impossible past. The telescope captured light from galaxies that appeared too massive, too bright, too mature for their tender young age. It's like meeting a newborn who is already speaking in full sentences and reciting classic literature. This discovery rocked the foundations of modern cosmology and forced scientists to ask a very uncomfortable question. What if everything we thought we knew about the birth of our universe isn't quite right? In this sleep lecture, we are going to journey back over 13 billion years into the past, right to the very cosmic dawn. We'll try to understand exactly what the James Webb saw, why it caused such a huge stir, and what bold, almost fantastical theories are being developed right now to explain this paradox, the light from the impossible past. Get ready, we're about to peer beyond the horizon of the known world. Before we dive into the mystery itself, let's tune our instruments and clarify some fundamental concepts. Without this foundation, our journey won't make sense. The main character in our story is light. Light travels at a finite, albeit incredibly fast, speed, nearly 300,000 kilometers per second, or about 186,000 miles per second. This means that light from any object doesn't reach us instantaneously. For instance, sunlight takes about 8 minutes to reach Earth. So, when you look at the sun, you are seeing it as it was 8 minutes ago. For distant stars, we're talking about years, thousands, or even millions of years, and for other galaxies, billions. A telescope, therefore, isn't just a magnifying glass, it is a genuine time machine. The further we look into space, the deeper we are gazing into the past. And that's exactly what the James Webb Telescope was built to do. See the very first stars and galaxies that ignited after the Big Bang. But how do we accurately gauge how far away a galaxy actually is? This is where a phenomenon called redshift comes into play. The universe is constantly expanding, and this expansion stretches space itself. As light from a distant galaxy travels toward us through this stretching space, its waves are also stretched out. This increases the wavelength, shifting the light toward the red, or longer wavelength, end of the spectrum. The further away the galaxy is, the longer its light took to reach us, the more space expanded along its path, and the greater its redshift. By measuring this redshift, astronomers can calculate the object's distance with incredible precision, telling us exactly how many billions of years into the past we are truly looking. These two principles, the finite speed of light and redshift, are the foundation of all early universe observations, and they hold the key to understanding our paradox today. So let's take a closer look at our primary tool for discovery, the James Webb Space Telescope. It's not merely the successor to the famous Hubble, it represents a generational leap forward in technology. If Hubble was our window onto the universe, Webb is a true portal to the past, specifically designed to capture the very first light emitted after the Big Bang. Its primary mirror, coated in a thin layer of gold, spans 6.5 meters in diameter, nearly 3 times wider than Hubble's. It's composed of 18 hexagonal segments that unfolded in space like some kind of gigantic, high-tech origami flower. This massive size allows it to collect far more light, enabling us to see dimmer and more distant objects than ever before. But Webb's most crucial feature is its ability to see in the infrared spectrum. Remember when we talked about redshift? The light from those earliest galaxies has traveled billions of years to reach us, stretching so dramatically that what started as visible and ultraviolet light has transformed entirely into infrared. Hubble could barely detect this, its vision was restricted. Webb, however, is the ultimate infrared specialist. For its sensitive detectors to function, they must be cooled to extremely low temperatures, almost absolute zero, down to -233 degrees Celsius. Any heat, whether from the telescope itself, the Sun, or the Earth, would act as blinding noise, overwhelming the signal. That's why Webb is equipped with a gigantic 5-layer sunshield, roughly the size of a tennis court, constantly protecting it from all sources of heat. Crucially, it's not in low Earth orbit, like Hubble. Instead, it sits 1.5 million kilometers away from Earth, at what is called the L2 Lagrange point. Here, the gravitational forces of the Sun and Earth balance out, allowing the telescope to remain stable and perpetually shielded in our planet's shadow. All these engineering marvels were created with one main goal: to peer into the era of the cosmic dawn and answer the question of how and when the first lights in the universe switched on. What nobody expected was that the answers it started sending back would, in turn, generate even bigger, even more fundamental questions. Let's take an even deeper dive into the further away means earlier concept, as it is absolutely fundamental to our investigation. Imagine the universe is a vast ocean and we are sitting on the shore. When a distant ship sends a light signal, we don't see it the moment it was sent, but only after the time required for that light to cross the distance between us. Now imagine this ocean is constantly expanding, causing all the ships to move farther apart. The farther away a ship is, the faster it recedes from us. This is our expanding universe. Light emitted by a galaxy billions of years ago begins its journey toward us. While it travels, the very space between that galaxy and us is stretching. The galaxy isn't merely flying through space, rather, space-time itself is carrying it away from us. You can compare this to a runner on an expanding treadmill. He is running at a constant speed, but the finish line is constantly being pushed farther back. This is why light from the most distant objects requires billions of years to reach us. When we look at the Andromeda Galaxy, our nearest major galactic neighbor, we are seeing light that traveled for 2.5 million years. We are seeing its past. When the Webb telescope looks at a galaxy with a redshift of, say, Z equals 10, it sees light emitted when the universe was only about 480 million years old. That is incredibly young, considering its current age of 13.8 billion years. This is the universe's cosmic infancy. Essentially, Webb is performing a kind of cosmic archaeology. Every layer of distance is a layer of time. By observing galaxies at varying distances, astronomers can piece together the complete evolutionary history of the universe, from the first clumsy groupings of gas and stars to the majestic spiral galaxies like our own Milky Way. Astronomers expected that in the deepest depths of time they would find something incredibly primitive, small, and chaotic. But when they finally dug down to this earliest layer, they were in for a shock. Instead of primitive huts, they discovered fully developed cities. And this shatters the entire chronology of cosmic construction that they had so painstakingly built over decades. Now let's turn to our main measuring tool, redshift. At first glance, this might sound like complicated physics, but the underlying concept is actually quite elegant. Remember the changing sound of an ambulance siren? The pitch is higher as it approaches and lower as it moves away. That's the Doppler effect. The same principle applies to light. If a light source moves away from us, its light waves get stretched out, the frequency drops, and they shift toward the red end of the spectrum. If it approaches, they shift toward the blue. However, in cosmology, we are dealing with a slightly different phenomenon, cosmological redshift. Here, the shift isn't caused by a galaxy speeding through space, but rather by the expansion of space itself, as we've discussed before. Imagine drawing a wave on a rubber band and then stretching it out. The wave itself gets longer. Similarly, a photon traveling through the expanding universe gets stretched along with it. Redshift, which is denoted by the letter Z, tells us exactly how much the universe has expanded during the light's journey from the source to us. If Z equals 1, it means the universe has doubled in size since that light was emitted. If Z equals 2, it has tripled. The most distant objects that the Webb telescope observes can have a Z value greater than 10 or even 13. This means that at the moment these galaxies emitted the light we see today, the universe was 11 or 14 times smaller than it is now. This represents an incredibly dense, hot, and young state. To measure this shift, astronomers use spectroscopy. They disperse the light from the galaxy into a spectrum, or a rainbow. Within this spectrum, there are dark lines, absorption lines, that correspond to specific chemical elements within the galaxy's stars. We know the exact wavelength where these lines should appear in a laboratory here on Earth. By comparing their laboratory, or rest position, to their position in the distant galaxy's spectrum, scientists calculate how far they have traveled toward the red end, thus determining the value of Z. This is the gold standard for measuring cosmic distances, and it is precisely these measurements applied to the objects found by Webb that have led to such staggering results. The spectroscopic data confirmed that these galaxies are truly located at the edge of the observable universe in its profound past. Therefore, their surprising maturity is neither a mistake nor a mirage. It is a fundamental reality that urgently requires explanation. To truly grasp why these new discoveries were so shocking, we first need to understand the accepted view of the cosmos that existed before them. This framework is known as the Standard Cosmological Model, or Lambda CDM, SATS Lambda CDM. It's more than just a theory, it's the culmination of decades of observations, calculations, and rigorous testing. Crucially, it describes our large-scale universe with astonishing accuracy. According to this model, our universe is composed of three main ingredients. The first ingredient is ordinary or baryonic matter, the stuff that makes up you and me, planets and stars. Surprisingly, this familiar material accounts for only about 5% of the total mass energy of the universe. The second and much more significant component is dark matter, making up roughly 27%. We don't know exactly what it is. It neither emits nor absorbs light. However, its gravitational influence is undeniable. It prevents galaxies from flying apart and forms a colossal cosmic web, the scaffolding upon which galaxies cluster and grow. In the TUNT Lambda CDM model, this is specifically designated as cold dark matter, CDM, meaning it consists of slow-moving particles. This characteristic is crucial because only cold matter can easily clump together, forming the necessary gravitational seeds for future galaxies. And finally, the third, most mysterious, and ultimately dominant component is dark energy, accounting for about 68% of the universe's entire mass energy density. Represented by the Greek letter lambda, SATS lambda, dark energy is responsible for the accelerated expansion of the universe, acting almost like an anti-gravity force, pushing space itself apart. The BOST Lambda CDM model successfully explains things like the cosmic microwave background radiation, the large-scale structure of the universe, and numerous other observations. Critically, it also makes very specific predictions about how the first structures should have formed. According to this model, structure formation was hierarchical, a bottom-up process. Tiny clumps of dark matter should have formed first. These clumps then drew in ordinary gas, leading to the formation of the first stars and dwarf galaxies. Over hundreds of millions and billions of years, these smaller galaxies were expected to merge slowly, aggregating into progressively larger structures. The model strictly predicted that the early universe should be populated by countless small, faint proto-galaxies, not the fully formed giants that the Webb telescope observed. Let's now fast forward to the very epoch the James Webb Space Telescope was designed to explore, the era of cosmic dawn. After the Big Bang, the universe was a hot, dense soup of elementary particles. Gradually, it expanded and cooled. About 380,000 years later, it had cooled enough for protons and electrons to combine into neutral atoms of hydrogen and helium. The universe became transparent to light, and that first illumination is what we now observe as the cosmic microwave background radiation. But that transparency was followed by the so-called dark ages. The universe was filled with neutral gas. Stars had yet to form, and absolute darkness reigned. This period lasted, according to various estimates, between 100 and 200 million years. During this time, gas began collecting in clumps of dark matter, collapsing under gravity until the very first stars ignited in their centers. This was the true cosmic dawn. Theorists had predicted the nature of these first stars, known as population stars. They should have consisted exclusively of hydrogen and helium, simply because heavier elements did not yet exist anywhere in the cosmos. Because of this composition, they were expected to be incredibly massive, hundreds of times heavier than our Sun, extremely hot and luminous, yet with very short lifespans, lasting only a few million years. Exploding as supernovae, these stars would have been the first to scatter heavy elements, carbon, oxygen, and iron, throughout space. These elements would then go on to form the next generations of stars, planets, and ultimately us. The earliest galaxies, according to the Standard Model, were predicted to be small, dim, populated by these first-generation stars, and extremely poor in heavy elements, or metal poor. Subsequently, light from these first stars and galaxies began to ionize the surrounding neutral hydrogen, converting it back into plasma. This process is called reionization, and it rendered the universe transparent, just as we see it today. Webb was designed to witness this monumental process, to observe those first tentative sparks of light punching through the fog of the Dark Ages. It was meant to confirm this beautiful and logical cosmic narrative, but as often happens in science, reality turned out to be far more surprising and complex. The moment of truth had arrived. As part of the JWST Advanced Deep Extragalactic Survey project, the James Webb Space Telescope spent hours, dozens of hours, gazing intently at a tiny patch of sky known as the Hubble Deep Field. This is one of the most studied locations in the cosmos, but Webb viewed it in a completely new light, infrared. And among the thousands of distant galaxies it spotted, several candidates showed off the chart's redshift values. Z was registering 11, 12, and even 13. The most famous of these objects was named JWST-0. Its light traveled for 13.4 billion years to reach us. We are seeing it as it was when the universe was only 330 million years old. This set a new record, the most distant spectroscopically confirmed galaxy ever observed. However, the shocking part wasn't the distance itself, but the unexpected properties of this galaxy and others like it. They weren't small and dim, as prevailing theory predicted. They were surprisingly bright and massive. The stellar mass in some of these galaxies was estimated to be billions of solar masses. That is an enormous amount for such an early period. According to the Standard Model, the universe had a specific budget of normal matter available for star formation at that time. These galaxies, however, seem to have managed to convert nearly 100% of their available gas into stars. This represents an extremely rapid and intense burst of star formation, a process the prevailing theory did not anticipate. Furthermore, these weren't merely chaotic clumps of stars. Some of them, such as the galaxy Sears 2112, discovered in a separate survey, already possessed organized structure resembling a barred spiral galaxy, just like our own Milky Way. By all calculations, the formation of such a complex structure should take billions of years of gravitational interaction, not just a few hundred million. Astronomers checked the data again and again. They looked for errors, for potential alternative explanations, but the numbers were stubborn. They were staring at objects that, according to the dominant cosmological model, simply should not exist. They were too large, too bright, and too complex for their age. This was truly the light from an impossible past. Let's take a closer look at the first conundrum, the mass paradox. Where did all this building material come from, gathered in one place in such a surprisingly young universe? As we recall, the standard lambda-CDM model postulates a hierarchical structure formation. Think of it like building a sandcastle on the beach. You can't just build a giant fortress instantly. First, you gather small piles of sand, then merge them into bigger mounds, shape the turrets, and finally connect them with walls. It's a slow, step-by-step process. In the cosmos, dark and baryonic matter play the role of the sand, and the force collecting them is gravity. Gravity is a weak force, and it requires a significant amount of time to pull matter together from vast volumes into dense structures. The model predicts that during the first few 100 million years, only small dark matter halos could have formed, perhaps only 1 million or 10 million solar masses. These halos, in turn, would attract enough gas to form dwarf galaxies. But Webb discovered galaxies whose stellar mass, meaning the mass of the stars alone, excluding gas and dark matter, already reached 1 billion, and in some cases 10 billion solar masses. To create that many stars, the original cloud of gas and dark matter would have needed to be 10 to 20 times more massive. This implies that within just 300 or 400 million years after the Big Bang, dark matter halos weighing hundreds of billions of solar masses must have already formed. Based on lambda CDM calculations, this is nearly impossible. There simply wasn't enough time. It's the equivalent of trying to build a skyscraper overnight with just a handful of workers and a couple of shovels. This suggests three possibilities. Either our calculations for the speed of this cosmic construction are incorrect, or the early builders had some advanced, unknown tools, or the foundation itself was laid down much earlier than we currently assume. This mass paradox became the first and most serious challenge to the established cosmological framework. It indicated that either the galaxy assembly process in the early universe was exponentially faster than we ever imagined, or there is something fundamentally wrong with our assumptions about the universe's composition and evolution. The second paradox, and it is equally astonishing, is the paradox of maturity. This isn't just about how massive these galaxies were, but about their appearance. Theory predicted that the earliest galaxies should look like clumsy, clumpy, asymmetrical blobs, the messy result of chaotic mergers and violent star formation. We expected to see cosmic tadpoles, not well-formed structures. However, Webb showed us something quite different. Some of these ancient galaxies, like the aforementioned Sierras 2112, exhibit a surprising degree of order. They possess a bright center, or bulge, and even a distinct disk structure with hints of spiral arms and a central bar. In modern galaxies, like our own, the disk and spiral arms are the result of protracted gravitational evolution. Stars and gas in these systems orbit within a single plane, much like a carousel. It takes billions of years to calm the chaotic motion of gas and stars following mergers and settle them into an ordered disk. Finding such intricate structure in a galaxy that is only a few 100 million years old is a profound mystery. It's like finding a perfectly cut diamond where you expected an unrefined lump of coal. Furthermore, the color of these galaxies also suggested maturity. They were not as blue as conventional theory predicted. Blue color in galaxies is typically associated with young, massive, and very hot stars. Redder hues, conversely, can indicate either large amounts of obscuring dust or the presence of older, less massive, and cooler stars. Analysis of the light from these early galaxies revealed that they seemed to possess a mixed stellar population, including not just the first generation, but also the second. This implies that the entire life cycle, star birth, death, chemical enrichment of the interstellar medium, and rebirth of a new star had already completed multiple times. And all of this occurred in a cosmically record-breaking short span of time. This unexpected structural and stellar maturity further compounds the problem. It is one thing to rapidly assemble a great deal of matter in one location. It is quite another to manage in the same time frame to shape that matter into a complex, ordered structure while simultaneously running through multiple cycles of stellar evolution. The third piece of the puzzle lies hidden in the chemical composition of these ancient star systems. And to understand this, we must first talk about metals. In astronomy, metals are simply defined as any chemical element heavier than hydrogen and helium. This includes carbon, oxygen, nitrogen, iron, essentially everything that makes up planets and, well, us. However, these elements were not created during the Big Bang. The Big Bang produced only hydrogen, helium, and trace amounts of lithium. All the other elements on the periodic table were cooked up in the thermonuclear furnaces of stars and then scattered throughout the cosmos when those stars exploded as supernovae. Every new generation of stars is born from gas enriched with metals from previous generations. Therefore, a galaxy's chemical composition acts like a passport that reveals its age and star formation history. Young galaxies should be extremely metal-poor, meaning they contain very few heavy elements. Older, more developed galaxies like the Milky Way are rich in metals. When the Webb telescope analyzed the light spectra from these impossible galaxies, it found traces of carbon and oxygen. This wouldn't have been a shock on its own, since the first massive stars should have quickly produced these elements. But the sheer quantity of these elements, coupled with the presence of cosmic dust, which is also made of those same heavy elements, was far higher than expected. Accumulating that much metal and dust would require several generations of massive stars to have already been born, lived their short lives, and exploded. This dramatically compresses the timeline even further. The process of chemical enrichment in the universe, which was thought to be slow and gradual, seems to have progressed at a frantic, turbocharged speed in its earliest corners. Where did this acceleration come from? Perhaps the first stars were even more massive, producing metals much more efficiently than our current models suggest, or maybe there were exotic types of stellar explosions we don't yet know about. This chemical fingerprint of time left in the spectra of ancient galaxies is yet another critical piece of evidence in our cosmic detective story, strongly suggesting that the early chapters of the universe's history need to be rewritten. Hidden at the core of most modern galaxies, including our own, are true monsters, supermassive black holes. These colossal objects weigh millions or even billions of times the mass of our Sun. It's generally accepted that they grow in tandem with their host galaxies, and their mass is closely linked to the mass of the galaxy's central hub, or bulge. But how did they appear? There are two main theories. The first, known as the light seed model, suggests that they grew out of stellar mass black holes, which were remnants left behind after the very first stars exploded. These seeds then gradually gained mass by absorbing gas and merging with other black holes, a relatively slow process. The second theory, the heavy seed model, proposes that the earliest black holes formed much faster via the direct collapse of gigantic gas clouds, completely bypassing the stellar stage. This would immediately create black holes tens or hundreds of thousands of solar masses in size. Now, the James Webb Space Telescope, or simply Webb, is throwing a wrench into this established picture. It has detected signs of active supermassive black holes in some of the most distant and earliest galaxies, SMBHs that already weigh millions of times the Sun's mass. These objects are simply too massive for their age, especially if they originated from light seeds. There wasn't enough time for such explosive growth. Even the heavy seed scenario faces difficulties, as it requires very specific and rare conditions in the young universe. Webb's observations suggest that supermassive black holes likely emerged much earlier and grew far faster than previously theorized. Some scientists are even proposing that the relationship might be entirely reversed. Perhaps galaxies didn't give birth to black holes. Instead, these colossal black holes served as gravitational anchors around which galaxies began to form. This radically turns the standard cosmological model on its head. But what if these seeds were even more ancient? There is a hypothesis concerning primordial black holes which could have formed not from stars, but from density fluctuations in the very, very early universe, within the first fractions of a second after the Big Bang. If these existed, they would be the perfect ready-made seeds to jumpstart the rapid growth of both galaxies and their central monsters. The challenge is that the existence of primordial black holes has yet to be proven. Thus, the mystery of these impossible early galaxies is inextricably linked to the origin of supermassive black holes. Solving one puzzle will most likely provide the key to unlocking the other. Faced with such a multitude of paradoxes, the scientific community began generating hypotheses, attempting to save the existing situation without tearing down the entire edifice of modern cosmology. The first and most conservative group of hypotheses suggests that we might have fundamentally misunderstood the physics of the very first stars. Perhaps the standard model of the universe is generally correct, but our models of star formation under the extreme conditions of the early cosmos are flawed. As we recall, the first stars, known as Population 3, were expected to be extremely massive and composed solely of hydrogen and helium. But what if they were even more extreme than we previously imagined? Some models hypothesize the existence of superstars or quasi-stars that could reach tens or even hundreds of thousands of solar masses. Such gigantic stars would burn incredibly brightly, far more luminous than typical star clusters. Perhaps what we are interpreting as an entire galaxy containing a billion stars is actually just one or a few of these superstars surrounded by an accretion disk. This could explain the anomalous brightness of the observed objects. We aren't necessarily seeing mass, we are seeing excess luminosity. Furthermore, these stars would produce heavy elements and explode with incredible power, potentially accounting for the rapid chemical enrichment observed. Another idea posits that the efficiency of star formation in the early universe was vastly higher. Today, in our galaxy, only a small fraction of the gas in a molecular cloud turns into stars. The rest dissipates. But what if, in the early universe, where the gas was denser and purer, this process was nearly 100% efficient? This would allow for a rapid buildup of stellar mass. These hypotheses are appealing because they do not require us to revise the fundamental laws of physics or cosmology. They merely suggest that nature, under these extreme conditions, behaves more ingeniously than we are accustomed to thinking. The problem is that the existence of such exotic stars remains purely theoretical for now. We need more detailed spectroscopic data from Webb to try and distinguish the light coming from a cluster of regular stars versus the light from a single hypothetical superstar. This remains one of the primary goals for future observations. If the problem isn't with the stars themselves, then perhaps the culprit lies in the universe's most mysterious component, dark matter. In the standard lambda CDM model, dark matter is considered cold. This means its particles move slowly and readily, clumped together under gravity, forming dense halos ranging in size from the tiny to the truly massive. This characteristic is precisely what drives the hierarchical, bottom-up model of structure formation. But what if dark matter isn't completely cold? What if it possesses some extra properties that we simply haven't discovered yet? For instance, there's the warm, dark matter model. In this scenario, the particles move faster, which prevents them from forming those very small clumps. Instead, they only form larger structures right away. However, this model struggles to align with other observations, such as the distribution of dwarf galaxies orbiting the Milky Way. There are also more exotic ideas. Take, for example, self-interacting dark matter. In this model, dark matter particles don't just attract gravitationally, they can actually collide with one another, much like billiard balls. Such interactions could radically change the dynamics of halo formation, perhaps speeding up the collapse at their centers and accelerating the overall growth of galaxies. Another hypothesis suggests that dark matter could decay or even annihilate, releasing energy that might then influence the surrounding gas and stellar formation processes. We even have the concept that dark matter isn't a single type of particle at all, but an entire dark sector complete with its own set of particles and interactions. The core problem with all these hypotheses is that they remain highly speculative. We still haven't captured a single dark matter particle in a laboratory setting, nor do we know its fundamental properties. Webb's data could effectively act as a sort of cosmic collider for particle physicists. If the standard cold dark matter model genuinely cannot account for these early galaxies, it would provide powerful evidence that the nature of dark matter is more complex than we currently assume, offering a clear direction for future research. This might hold the key not only to the mystery of galaxy formation, but also to entirely new physics beyond the standard model of particle physics. Let's dig even deeper, right back to the very first moments of the universe. The standard model tells us that the Big Bang was immediately followed by a period of incredibly rapid expansion, known as cosmic inflation. In mere fractions of a second, the universe ballooned from subatomic size to roughly the size of a grapefruit. Inflation explains key features of our cosmos, why it is so vast, so uniform, and so flat. Crucially, it also explains the origin of structure. Tiny quantum fluctuations present during this period were stretched out to astronomical scales, becoming the initial seeds of density from which all future galaxies and clusters would eventually grow. The standard inflationary model predicts that these initial fluctuations were distributed almost uniformly across all scales. This distribution leads to the slow, hierarchical growth of structure we observe today. But what if inflation wasn't quite so smooth? What if there were irregularities in the inflationary field that led to the formation of not just small seeds, but several large megaseeds of density right from the start? These so-called non-Gaussian fluctuations would have created gigantic, superdense regions in the early universe. These regions would have begun collapsing much earlier and much faster than the standard scenario suggests. This could explain why we observe massive galaxies so early in cosmic history. Instead of growing slowly from cosmic villages, they simply began life in cosmic megacities. Another intriguing idea involves the possible formation of primordial black holes during or immediately after inflation. If density fluctuations in certain areas were extremely large, those regions might collapse directly into black holes, skipping the stellar formation stage entirely. These primordial black holes could act as the heavy initial seeds we discussed, kickstarting an accelerated rate of galaxy formation. These hypotheses are fascinating because they bridge observations on the largest cosmological scales, thanks to Webb, with the physics of the highest energies and smallest scales, inflation itself. If the Webb data truly force us to revise the standard picture of inflation, it would spark a revolution not only in cosmology but in fundamental physics as a whole. The difficulty is that directly testing these ideas is incredibly challenging, but anomalies in the distribution of these early galaxies might be the indirect evidence we've been searching for. Now we come to the boldest, most radical, and perhaps the most exciting hypothesis of all. What if the problem isn't with the stars or dark matter or cosmic inflation? What if the issue lies with our cosmic clock? What if the universe is actually far, far older than we currently believe? The current estimate for the age of the universe, 13.8 billion years, is derived from measuring its expansion rate, the Hubble constant, and extrapolating that expansion back in time to the moment of the Big Bang singularity. This age fits perfectly with the oldest stars in our galaxy and aligns with other cosmological data within the standard lambda CDM model. But what if that model is incomplete? Dr. Rajendra Gupta, a physicist at the University of Ottawa, has proposed a hybrid model that attempts to explain the Webb anomalies by effectively doubling the age of the universe to 26.7 billion years. How is this possible? His model combines two major yet historically controversial concepts. First, he revives the old, almost forgotten, tired light hypothesis, originally proposed by Fritz Zwicky back in 1929. Zwicky suggested that photons, as they travel through the cosmos, somehow lose energy, which causes the observed redshift. This loss of energy is entirely independent of the universe's expansion. Second, Gupta integrates the concept of evolving fundamental constants, an idea originally put forward by Paul Dirac. In this view, the fundamental forces of nature, such as gravity or electromagnetism, may have been different in the past. In Gupta's model, the redshift we observe is a combination of two effects: the genuine expansion of the universe and this proposed tired light. The evolving constants, in turn, stretch out the time required for galaxy formation. In this aged-up universe, the earliest galaxies would have had not just 300 to 400 million years to develop, but several billion. That amount of time would be more than enough for them to grow to the observed sizes and maturity. This hypothesis is admittedly true heresy for modern cosmology, as it requires overturning our most fundamental assumptions, but it elegantly solves the problem of the impossible galaxies. The lingering question is whether, in solving one problem, it creates far more complex issues in other areas of physics. Before we get too carried away with the idea of an aged universe, let's quickly address why the tired light hypothesis was rejected by the scientific community decades ago. It has several fundamental issues that are very difficult to circumvent. First, if photons simply lose energy as they travel, distant objects shouldn't just look redder, they should also look blurry. The particles or fields that photons interact with to get tired would have to change their direction, scattering them. However, observations show that images of distant galaxies and quasars remain strikingly sharp, which contradicts most tired light models. Secondly, and this is arguably the strongest argument, is the observation of type T supernovae. These white dwarf explosions are excellent standard candles for cosmologists because they always have approximately the same peak brightness. By observing them, astronomers noticed something remarkable. The farther away a supernova is, and the greater its redshift, the slower the explosion process itself appears to unfold. The light curve, the way the supernova's brightness rises and falls over time, is stretched out. This time dilation effect is perfectly explained within the framework of an expanding universe. Time itself, in a distant, rapidly receding frame of reference, appears to move slower for us. The tired light hypothesis simply cannot account for this phenomenon. If the universe weren't expanding and light was just aging, we wouldn't see any time dilation at all. Thirdly, there is the spectrum of the cosmic microwave background, or CMB. It matches the spectrum of a perfect black body with incredible precision. This is a natural consequence of the Big Bang model, where the early universe was in thermodynamic equilibrium. In a static universe relying on tired light, it is extremely difficult to explain why the CMB would have this exact shape. It is precisely because of these and other inconsistencies that the original tired light hypothesis was essentially buried. Rajendra Gupta's model attempts to circumvent these issues by combining tired light principles with expansion and evolving constants, but the scientific community currently views it with significant skepticism. For such a revolutionary idea to be accepted, it must not only explain new data from James Webb, but also remain consistent with the enormous body of data upon which modern cosmology rests. The notion that the standard lambda CDM model isn't the final answer in cosmology has been around for quite a while, despite widespread skepticism. Several alternative models exist. They attempt to resolve not only the mystery of early galaxies, but also other uncomfortable issues, such as the persistent discrepancy in measurements of the Hubble constant. One of the most elegant and unconventional of these ideas is conformal cyclic cosmology, or CCC, proposed by the renowned physicist Roger Penrose. According to CCC, our universe is just one eon in an infinite sequence of cosmic births and deaths. The end of one eon, when the universe has expanded into a cold, empty void, is mathematically transformed into the Big Bang for the subsequent eon. In this model, information from the previous cycle can leak into ours, perhaps manifesting as giant primordial black holes that could serve as the seeds for galaxy formation. This theory doesn't necessarily make our current universe older, but it strongly suggests that its initial conditions were inherited or shaped by the previous cosmic cycle. Other models propose that dark energy, the very lambda term, represented by our lambda dollars, is not a constant. Its density might have changed over time. For instance, early dark energy could have existed in the primordial universe, accelerating expansion before decaying away. This dynamic process would directly influence the rate of structure formation. These frameworks are generally known as models featuring evolving dark energy, or quintessence. Then there are modifications to the theory of gravity itself. It's possible that on cosmological scales, gravity doesn't strictly follow Einstein's general theory of relativity. Theories like MOND or FR gravity attempt to explain observed effects, such as galactic rotation and accelerated expansion, without needing to invoke dark matter or dark energy. However, currently, none of these alternatives can describe the full suite of cosmological observations with the same precision and consistency as lambda CDM. New data from the James Webb Space Telescope could provide the crucial impetus needed to force theorists to take these alternatives more seriously, potentially leading to the creation of a new, more complete standard model that incorporates both the past successes and the new, unexpected discoveries. Before we officially declare a crisis in cosmology, let's take a step back, put on our skeptic hats, and ask the essential question: could we simply be measuring or interpreting something incorrectly? Science must always leave room for doubt, especially when we are dealing with such revolutionary claims. First, let's consider instrument calibration. The James Webb Space Telescope is an incredibly complex piece of equipment. While it has been calibrated with the highest possible precision, there is always the potential for slight systematic errors that could affect the measurement of brightness or color in distant objects. For instance, if we slightly underestimate the amount of dust Within those early galaxies, we might be inadvertently overestimating their stellar mass. Dust absorbs blue light and re-emits it in the red spectrum, making the galaxy appear redder and, at first glance, older and more massive than it truly is. Second, stellar population models. To determine a galaxy's mass from its color and brightness, astronomers rely on sophisticated computer models. These models simulate how the light from millions of stars of varying ages and chemical compositions combines. They are based on our current understanding of stellar evolution, but, as we've discussed, our comprehension of the very first metal-poor stars might be incomplete. If those early stars were significantly brighter or lived longer than we currently assume, our mass estimates could be heavily inflated. Third, the uncertainty factor. We must remember that we are observing objects right at the very limit of our instrument's capabilities. The signals we receive are extremely faint, and the measurements are inherently prone to error. What currently appears to be a giant galaxy might, after longer observation periods and more detailed analysis, turn out to be something less extreme. The scientific community is currently working actively to address all these questions. Different research teams are analyzing the exact same data using varying methods and models to rule out any potential errors. This is a normal, healthy scientific process. Only if the anomaly persists after all these rigorous cross-checks and verifications can we confidently discuss the need for new physics. Perhaps the panic is premature and the solution lies simply in fine-tuning our existing instruments and models rather than tearing them down entirely. Another effect that can significantly distort how we perceive the distant universe is gravitational lensing. According to Einstein's general theory of relativity, massive objects like galaxies or clusters of galaxies warp the surrounding space-time. Light from more distant objects passing close to such a gravitational lens bends its trajectory, much like light passing through a traditional glass lens. This effect can lead to surprising consequences. It might create multiple images of the same distant object, distort its shape, stretching it into arcs and rings, and, most importantly for us, it can significantly amplify its brightness. A gravitational lens essentially acts as a natural telescope, enabling us to see objects that would otherwise be far too faint. So could it be that the impossible galaxies observed by the Webb telescope aren't actually that massive or bright? Perhaps their light was simply boosted by some massive but invisible structure located along the line of sight between us and them. This is entirely possible. Astronomers always factor in this probability. They meticulously check the environment of every ultra-distant galaxy candidate for potential lenses, meaning visible galaxies or clusters. The issue is that the lens could also be just a clump of dark matter which we cannot see directly. However, strong lensing typically creates characteristic shape distortions, which are absent in many of these impossible galaxies. They appear quite symmetrical. Of course, there is always the possibility of weak lensing, which only slightly increases brightness without drastically distorting the shape. Some studies suggest that accounting for this effect could shift the most extreme candidates back into a range more or less compatible with the standard cosmological model. Nevertheless, most scientists believe that lensing cannot be the universal explanation for the entire population of these strange objects. There are simply too many of them, and they are scattered across different parts of the sky. It is highly unlikely that we would be so lucky as to find that all of them just happen to be positioned behind a lens. Still, it remains a crucial factor that must be carefully modeled and accounted for during data analysis, helping us separate the true properties of these ancient galaxies from illusions created by cosmic mirages. What we are witnessing today is not a crisis or the end of cosmology. Quite the opposite. This is science at its most thrilling and best. It's a moment when nature throws us a puzzle that doesn't fit the existing framework, forcing us to think, innovate, and rigorously test new ideas. Let's look back at the history of science. In the late 19th century, many physicists believed that the picture of the world was essentially complete. Newton's classical mechanics and Maxwell's electrodynamics seemed to explain everything, but a few little clouds on the horizon remained: the blackbody radiation problem and the results of the Michelson-Morley experiment. These little clouds ultimately led to the two greatest revolutions in physics, the creation of quantum mechanics and the theory of relativity. Perhaps the James Webb Space Telescope's impossible galaxies are our modern-day clouds on the horizon. We are currently in the stage of data collection and hypothesis generation. Different groups of scientists are proposing explanations, ranging from the highly conservative to the extremely radical. Every single hypothesis must be rigorously tested. For example, if the issue lies in our stellar models, we need more detailed spectra to find the chemical fingerprints of these exotic stars. If the problem is rooted in dark matter, we need to search for its manifestations in other astrophysical phenomena. And if the hypothesis of a much older universe holds true, it must make verifiable predictions, perhaps observable in the cosmic microwave background data. This entire process is like detective work. We have a crime scene, the unexpected data, and we have suspects, the various hypotheses. Now we must gather the evidence, cross-examine the facts, and check the alibis. Every new scientific paper, every new observation is another crucial step in this ongoing investigation. Even if the ultimate explanation turns out to be somewhat prosaic, for instance, we simply underestimated the amount of cosmic dust, the very process of searching, debating, and verifying will make our science stronger and more precise. But if one of the radical ideas is confirmed, we will be witnesses to a scientific paradigm shift, much like those sparked by Copernicus, Newton, and Einstein. And that makes this an incredibly exciting time to be interested in cosmology. So, what lies ahead? How are scientists planning to untangle this complex puzzle? The main key to solving this mystery lies in deeper, more detailed observations. Webb's initial discoveries were based on photometry, measuring the brightness of objects through various filters. This method provides a rough estimate of their redshift and properties. But to get an accurate diagnosis, we need spectroscopy, the technique of splitting light into its full spectrum, as we've already mentioned. The spectrum is essentially the galaxy's medical chart. It allows us to precisely measure the redshift, determine the chemical composition of the gas, estimate the age of the stellar population, calculate rotational speed, and detect the presence of an active black hole. In the coming years, Webb will dedicate hundreds of hours to acquiring deep spectra for the most intriguing candidates among these early galaxies. This data will allow us to rule out many hypotheses. For instance, we'll be able to tell definitively whether we are looking at a cluster of normal stars or a single superluminous star. We will be able to measure the abundance of metals and understand how quickly chemical enrichment occurred. We'll even be able to weigh their central black holes. Beyond Webb, other instruments are also ready to help. Next-generation ground-based telescopes, such as the Extremely Large Telescope, ELT, with its 40-meter mirror, will be able to study these objects with even greater resolution. The upcoming Nancy Grace Roman Space Telescope will conduct large-scale sky surveys, allowing us to find thousands of these early galaxies and build the necessary statistical base to differentiate random fluctuations from universal laws. Theorists, meanwhile, are not sitting idle. They are using supercomputers to create increasingly complex simulations of the early universe. They feed these simulations with different physical models, variations in the properties of dark matter, different types of first stars, and various inflation models. By comparing the results of these simulations with the real data from Webb, they will be able to determine which model best describes reality. This is a true synergy of observation and theory. Observations pose the questions, and theory offers potential answers that can then be tested through new observations. We are only at the very beginning of this journey. The puzzle of these impossible galaxies is not a dead end, it's an invitation to look deeper, to think bolder, and potentially to unlock a completely new, even more astonishing universe. So let's recap our long journey back to the dawn of time. The James Webb Space Telescope, that magnificent feat of engineering, peered further back into the past than any instrument before it, only to reveal things that, frankly, shouldn't have been there. It found galaxies that just a few 100 million years after the Big Bang were already surprisingly massive, incredibly bright, structurally complex, and chemically mature. This light from an impossible past presents a genuine challenge to the standard cosmological model, which has successfully described our universe for decades. We've explored a whole range of possible explanations. Perhaps we're simply wrong about the details, maybe the instruments were miscalibrated, or we're incorrectly modeling the properties of those very first stars. Maybe the solution lies with the mysterious dark matter, behaving in ways more complex than we initially thought. Or perhaps we need to revisit the very foundations, the theory of inflation that describes the universe's first moments, or even the established age of the cosmos itself, suggesting galaxies had significantly more time to develop. Each of these hypotheses leads us into new, uncharted territories of physics and astronomy. We don't have a definitive answer yet. And that is a wonderful thing, because it's exactly these kinds of mysteries that propel science forward. James Webb didn't break cosmology. It simply opened a brand new chapter for it, one full of intrigue, debate, and future breakthroughs. We are living in an extraordinary time, watching the map of the universe being redrawn right before our eyes. Thank you for spending this time with me diving into this incredible cosmic mystery. If you enjoyed this sleep lecture, please hit the like button and subscribe to the channel so you don't miss our next journey to the boundaries of knowledge. Now, I have a question for you. Which of these hypotheses seems the most plausible? Or maybe you have your own completely wild theory. Let me know in the comments below. Let's discuss it. Good night, and may you dream of distant galaxies.